Are you ready to rock, Squidward? No, that's the spirit. All right, this day is all about reaction types. Now, there are many different kinds of reactions, and some of them you don't go through in detail until second semester chemistry, but there are 5 basic chemical reactions that, doggone it, we just got to know. And also there's another basic kind of chemical reaction that we'll go through a little bit, but you get much more into second semester chemistry. So let's dive into the ones that we need to get into. There's 5 basic types. So before I get into the 5 basic types though, there is another kind of reaction which we should know. Now I'm going to do the very basic of this kind of reaction called an acid-base reaction. An acid-base reaction can get quite extensive. I mean, if you have what are called weak acids versus strong acids, you can do an awful lot of chemistry, and there is an awful lot of chemistry involved in acid-base reactions, a lot. But I'm just going to give you the very, very pinnacle tip peak of the iceberg with a basic acid, it's funny, basic acid-base, acid-base reaction. Fundamental acid-base reaction would be what's called a strong acid and a strong base reaction. So, for example, if you had a strong acid and a strong base, you will get an arrow goes in one direction. Sometimes chemical reactions have arrows going in both directions, and that means something. That's important. But in the case where you have a strong acid and a strong base, it's an arrow to the right, meaning this will always happen. You will get a salt and water. Salt and water. Water is a neutral substance and salt is salt, so you end up neutralizing. And you probably know that acid neutralizes base and vice versa, base neutralizes acid. Probably know that. If not, well, now you do, because they do. They neutralize each other. So let me give you an example, a quick example of an acid-base reaction. We have a strong acid, HCl. And I'm not going to talk about what a strong acid is at this point or a strong base, because there's no point in doing it because we don't get into acid-base chemistry per se like you would in later chemistry. But it is a strong acid, okay? HCl is strong acid, and sodium hydroxide is a strong base. And if this were to combine with this, what would happen is you would end up getting NaCl, that would be your salt, sodium chloride. And you'd end up getting some HOH, which is water. So salt and water. Right? So that would be an acid. So I do want you to know that reaction. I do want you to know a strong acid and a strong base will form a salt and water. That I do want you to know for acid-base chemistry. But that's it for now, okay? You stay tuned. If you go into second semester chemistry, which is awesome, then you will go mucho grande acid-base chemistry. All right, move on. So here are the 5 basic types, and this is a basic kind of reaction, but that's not what I'm calling like the 5 basic types. The 5 basic types of reactions that you and or I need to know. First type is called a synthesis reaction. A synthesizer puts sounds together. Well, a synthesis means to pull together to form something, and that's exactly what we're going to do here. In a synthesis reaction, we have you can have a compound in an element. You can have an element in an element forming one thing, and that's the key. In the synthesis reaction, you're going to have things coming together to form one thing on the right. Okay, now I'm going to give you a generic way of writing it, a generic way of expressing this. Okay, generically, A plus B equals AB. Stuff over here on the right just goes together and forms stuff on the left. Now, typically, it's usually, and for what we're going to be doing, it's going to be an element in an element. It can be an element in a compound, just hooking up and forming a larger compound. So you can do that. But for us, it's going to be element plus an element makes a compound. But the key is, in both of these generic ways of writing a synthesis reaction, is that you have one thing on the right. If you see one thing on the right of reaction, boom, synthesis reaction. Okay, let me give you an example. IRL example. You have, and I used this the other day when we were going over stoichiometry. Hydrogen, that's water. Hydrogen plus oxygen make water. And there is a balanced reaction. It's a synthesis reaction. You got your hydrogen element, your oxygen element coming together in forming that water. Boom. Easy peasy lemon squeezy. Very good. Yes. So synthesis. Piece o' cake. All right. Well, the opposite of bringing stuff together and forming something is breaking it apart. Decomposition is your second basic type. So that was type number one, synthesis. Decomposition is your second. Decomposition. Decomposition. It's French. Decomposition. See? French. Decomposition is the exact opposite of a synthesis. So what you have is you have something, one thing on the left breaking down and forming stuff. So the generic way of writing this would be the opposite of the synthesis. So it would be AB breaks down to form A plus B. Now the AB can be a large compound forming to form maybe an element in a compound or two other compounds. So that's possible. For what we're going to do though, it's going to be a compound. Always it's going to be a compound on the left and one on the left. So that's how you know you have a decomposition reaction. When you have one thing on the left. As soon as you see one thing on the left, decomp. All right, but we are going to have our decompositions go into elements and elements. So that's the generic way, two different generic ways of writing a decomposition. And we can go ahead and just do the opposite with the example I just did. We can take water and you can decompose water. Yes, you can. Yes, you can. I remember doing that in 8th grade. So we're talking like back in 1927. Yeah, I was in 8th grade back in 1927. Great year, great year. You know, doing Charleston. That was great. Awesome. I got moves. Where was I? Oh yeah, back in 8th grade, we decompose water. You do that by using electrolysis. As energy goes in and makes those things go, takes energy to do that because these like to form water and water does not want to break down, but you can do it. You got to put energy into the system. If you do that, you'll end up with hydrogen and oxygen. Of course, we want and in test tubes, those great little explosive sounds. Of course, when you're in 8th grade, you're like, yeah. Heck with 8th grade. I'm all like, yeah, when you get those explosions. And now, haven't grown out of it. All right, there's a decomposition reaction for you. Okay, now, I have uploaded. You have in your essential course documents a thing, a sheet, a paper that is called chemical reaction types. And I'm going to be going over a lot of those in the next video. And I'm just going to pick some out. We'll go through them for practice and examples. All right, let's keep going. Type of reaction number 3. You with me? Number 3. Okay, here we go. Double displacement. So double displacement. Double displacement. Displacement is also French for displacement. So now sometimes it's called double replacement. You might say it's double replacement. It's the same thing. All right, so what happens here? Let me write the generic form for you first. It's going to be a compound and a compound makes a compound in a compound. You're going to have two compounds on the left, you're going to have two compounds on the right every time. Okay, that's your generic form. Now, if we want to use the A's and B's, it gets a little complicated, but I'll show you how that would look. We get AB plus B's, can't be used B, CD. Okay, two different compounds. Then we end up with AD plus, so the A goes in here, kicks out the C, then the B and the D connect together. So your A and your D and your B and your C. So we end up getting kind of a switcheroo, it's a swap. Okay, ever see the story wife swap? Really annoying, you know, for the wives they swap families and the families all hate the wives, but then in the end they all love each other and stupid. But anyways, this everybody loves each other in chemistry swapping here. So what we got is we have an A coming in, kicking out a C, forming with the AD. That C goes back and it connects with this B. Actually, I should write this the opposite way because the C will be in front of the B. So we'll do it that way. And I'll explain why in just a second why that is. Okay, so I put the C. So we're just switching these two that are in front. So the C goes in front of the B, and the A goes in front of the D. Okay, well, give me an example. Maybe that'll help me out because I don't see what you're talking about, Willis. All right, this is actually a relatively easy reaction type and an easy one to predict product. And that's what we're going to be doing here. We're doing this so we can predict products. You're going to have chemical reactions and you have to predict what products will form. And the only way you can do that is you have to understand what kind of reaction it is, what type of reaction. If you know the type, you can predict the product. Okay, now double displacement might beg the question, is there a single displacement? Answer? Heckin' yeah, there is. There is a single displacement. Well, why didn't you teach that one to us first? It's only one, single versus double, so it's going to be easier. No, it's not. It's actually not. The single displacement reaction is the most difficult one to do, even though you only have one switch. Displacement means switch. Replacement means switch. Here we have a double switch, and that's easier than a single switch. And we'll go through why that is in just uno minuto grande. All right, finish this out. Let's do an example. Let's say that I've got some sodium chloride, and I have some lithium bromide. Okay, what's going to happen in a double displacement? When you have these two compounds in a compound, you're going to make a compound in a compound. And all you do, and this is actually why it's the easiest thing out of the displacement reactions, the easiest one is because you always take the metal and you switch spots. So the sodium is connected with chlorine, is going to switch places, kick out the lithium, hook up with the bromine, so sodium bromide, and then the lithium comes back. That's why I had to switch those two letters. I had the B in front and the C. In fact, that's wrong because you never write the metal second. The metal is always going to be written first. And so since lithium is the metal, okay, remember when you have a compound, the one on the left is a metal, the one on the right is a non-metal, and you have an ionic compound. So that lithium comes in, kicks out the sodium, or switches with the sodium, and goes and connects up with that chlorine. So that's why we had to put the C first here. All right, so we have lithium, and then switch, you've got chlorine. And this, I picked ions that I knew were all plus and minus one, so I didn't have to go through the process of balancing its balance. So that would be my double displacement reaction. Switch the metals, write the new products. That one's pretty easy. All right, we'll practice with that. We'll have some practice with this sheet of the stuff, and we'll go through them. So more practice in the next video. Let's go on to the next. All right, in this one I will now go with type number 4 is the single displacement. This one's a little more difficult. Single displacement. And let me write you the generic form for that. It's going to be an element plus a compound. Element plus a compound is going to make a compound and an element. And sometimes I'll get this question from students. Do I have to put the element first and the compound second? Can I put the compound plus the element? Or can I over here, instead of writing the product as compound and element, can I put compound, element and compound? Is that okay? Yeah, sure it is. I mean, what's 1 plus 2? Anybody got a calculator? It's 3. Okay. What is, that was 1 plus 2. What's 2 plus 1? 3. Oh, good thing I have my calculator with me, okay? That's tough math for today. So it doesn't make any difference what order you put these in. You have the same product, just you put one in front of the other. Typically, you will see it this way, though. You'll see the compound first and the element second. But it doesn't have to be that way. All right? Okay? All right? That's why the cool kids do it. Nobody's laughing at those cool kids. So now, some of you like the letters. I mean, they like the A's and the B's, so how would that look? All right. So it would be A plus BC, AC plus B. You ready? See, some of you like those. Yeah, I like those. See if you like it now. You ready? Check it out. A plus BC makes the A plus C. What the heck did you just do? I get this one, you move that in there, kick the B out, and you come in like that. I get that. Well, here I took the A and kicked out the C and put the B in back. Now, why would I do that? Because there are two different kinds of single displacement reactions. One is where a metal kicks out a metal, because remember, metals are first. A metal kicks out a metal, and then you end up getting that metal kicked out. This one, what happened here? The A kicked out the C, which is a non-metal, and then I ended up connecting the non-metal with the metal here and kicking out the non-metal C. So that is one where you have a non-metal. So you can have a single displacement reaction which involves metals and non-metals being replaced or displaced, and we got to think that through. The other thing we have to think through is, will the reaction actually happen? Will it happen? In other words, will this element be able to kick out something in that compound? Will the element here, this metal, be able to kick that metal out? Will it be able to do it? Or sometimes it can't. It can kick the metal out. It's trying to, but this metal says, no, I will not be kicked out. You may not let you do that to me. And down here, this non-metal is trying to kick out that non-metal, and sometimes this non-metal goes, no, I don't think so. No, I'm not leaving. And the other, this guy goes, meh, and it doesn't happen. That would be a no reaction. How are you supposed to know whether or not the metal or the non-metal can kick out in the compound, the metal or the non-metal? How are we going to know that? Okay, on your sheet today, you will see, they'll line up there, okay. Activity series, table 4.16. I call the activity series the spiffy chart. Some elements are more spiffy than others. Now, of course, spiffy isn't how chemistry is going to say that in your chemistry book, so I spiffy it up a little bit. So you have a spiffy chart, an activity series that is loaded into essential course documents for that. No, it's not going to be under spiffy chart. Okay, although it's in parentheses of spiffy chart, another activity series. So you look at that activity series, that's how you know if something can kick out something else, if something can replace something else. Now, how does it work? All right, the spiffy chart, I don't have one in front of me. It's over there, and it's too far for me to go grab it. Okay, so I'm not going to, but you have it in front of you. You can see it. You can see at the top, you have lithium. And then it goes blah, 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 all these metals. These are all metals. It's only showing you the metals on that chart. And they show you metal. You get down here, and you got things like gold and copper. Copper's down here. So some things are higher on the chart than others. Like sodium is pretty high up on the chart. You get some of these common metals that are down lower. You get iron, which is kind of in the middle a little bit. So you get some metals higher on the chart than others. So what does that mean? The higher you are, the more active you are. The more wild and crazy that you are, the higher up on that chart. And if you're wild and crazy, you can kick out somebody who's less wild and crazy than you. So you can kick out somebody below on the chart. So if I'm lithium and I look at silver, which is down here on the chart, I'm higher than silver. I'm more spiffy. I'm more active. I can kick silver out, but not the other way around. If you're lower on the chart than somebody else above you, you can't kick the person above you out. Only up top, you can kick the person down below out. So that's how we're going to know if a reaction can actually take place or not. We're going to look at the activity spiffy chart and see. It's kind of like this. Okay? Say I'm a metal. I mean, since I don't get as much activity anymore, I'm becoming heavy. You know what that means? I'm a heavy metal. Iron Maiden going on there. It was funny. Come on. So let's say that I am a metal. And I look over on the dance floor. And there's Giselle dancing with Tom Brady. Okay. So I'm going to go up to Tom Brady and say, "Hello, Mr. Brady, you mind if I dance with Giselle?" He's going to look at me and go, "No." And I'm going to go, so that would not be a replacement. I can't replace Tom Brady. He's just Tom Brady, okay? Even I have a crush on Tom Brady. Everybody does. Even though he's left to go to Tampa, he's still so hot. Oh, sorry, I shouldn't have said that in a video. Back the truck up. Where was I? Talking about Tom Brady's hotness. I can't kick Tom Brady out. Now, if it's the other way around, here's me dancing with Giselle in my dreams, okay? I'm dreaming. And then Tom Brady comes along. He is going to be able to say, "Out of here, buddy." And I will be, boom, kicked out over by myself, all by my lonesome, crying, as Tom now dances with Giselle. All right? So, that's kind of what happens here. Some elements are more spiffy than others. Okay? My spiffiness would be way down here on the spiffy chart. Okay? And Tom Brady's up here at lithium. Okay? All right. So, let's take a look at, let's do an example problem. So if we have an example problem, well, let's go ahead and use sodium and some iron chloride. Okay. Let's try this out and see if this would actually go through. Will this go through? Will this actually work? Will sodium be able to kick out iron? You go to your spiffy chart, check out and see. Sodium's up here, iron's farther down on the chart, isn't it? Yes. That means sodium is more spiffy. This is like Tom Brady, and that's me dancing with Giselle. Once again, I'm trying to, in my brain, imagine that I can't. It's not going to happen. But it's my dream, okay? And sodium, don't take my dreams away. So sodium comes in and goes, boom, you're out. I'm higher than you on the chart. I'm more active, spiffy. So you kick out. Now, what I'm going to do, you're going to watch me do this. I'm going to put in sodium with the chlorine. I am not going to carry the subscript. I'm not going to put the subscript down here. Don't do that, because it might be there, but it might not. It could be correct if I carried it, but it might not be correct. I'm going to have to figure it out myself. So don't carry subscripts when you make that switch. If you have a transition, something kicking out, just connect it with the element and leave it alone for now. Don't put subscripts in. Iron gets kicked out like that. Now I'd have to go and make sure I've written everything correctly. This iron must be using the +2 charge. How do I know that? Because chlorine's always a -1. There are 2 of them. So 2 times -1 is -2. It's a -2, so you have to balance that with a +2. So this must be iron 2 chloride. So they did a little review for you, formula writing. And then I kick the sodium out. Now sodium's a +1, chlorine's a -1. So we know that's correct for sodium chloride. You've seen that enough, you know that's sodium chloride. And that's why, because they balance each other out. All right, iron's on itself, by itself. Oh, the other thing you really got to pay attention to, diatomic molecules. If a molecule is by itself, you have to know your 777. The 7 diatomic molecules. You got hydrogen. All right, you remember that? Starts at, and then it goes, and then 7 on the periodic table. We showed you that. NOFClBri. Those are diatomic. Sodium is not a diatomic molecule when it's by itself. Now remember, diatomic is like hydrogen. You have 2 of them. You have to show that diatomic when it's by itself. Sodium is not one of those, so I leave it. Iron is not a diatomic, so I leave it. But we do have to make sure that we're aware of that. That'll come back to haunt and bite you in the butt if you don't remember those diatomics. All right, enough babbling. Balance it, okay, because I have 2 chlorines. So I'm going to put two here to balance the chlorine. That means I'm going to need 2 sodiums to balance here. So now I have a balanced reaction, and I predicted the product. Okay, this video is getting a little bit long, but you know what? I'm gonna keep this going. One more. What would happen if I had, because I just did this, I did the metal replacing the metal. What if a non-metal kicks out a non-metal? Do you have an example like that? I do. Here we go. What if we had fluorine and we had some potassium chloride? Okay, would this reaction happen? First thing you say to yourself is, this is single displacement, because I have an element and a compound. Single displacement. Boom. I said fluorine, I wrote iron. I want it to be fluorine. Fluorine, because I need a non-metal. So we're doing a non-metal example. Fluorine's a non-metal. It's going to try to kick out the non-metal. A non-metal has to kick out a non-metal. So trying to kick out the non-metal, can it do it? Well, I look at my spiffy chart and it's not on there. There aren't any non-metals on there. So how am I supposed to know who's more spiffy? Answer, look at your periodic table. Go ahead, get your periodic table, look at it. The higher up you are on your group, the higher up on the group, the more spiffy you are. Find fluorine. Fluorine's at the top of the halogen group. And it goes chlorine, bromine. It is the spiffiest of all of them. So fluorine is spiffier than chlorine. So fluorine can kick out chlorine. It's more spiffy. Okay, all right. So yes, fluorine being more spiffy, higher in its halogen group, can kick out the chlorine. So I will end up getting KF. Notice I did not bring the 2 here as a subscript. Okay, I might need it, but you don't drag it, you figure it out. Now this chlorine gets booted out. Okay, now that chlorine is off all by its lonesome. Rockets red glare bursting in air. You have to know the 777 diatomic elements when they're by themselves. Every time you see an element by itself in a chemical reaction, see if it's diatomic. Is chlorine one of the 777s? Is it one of, on our periodic table, hydrogen, or one of the seven started with number 7 that forms a 7, NOFClBri? The answer is yes. It is a 777 diatomic. So it has to get the 2 when it's by itself. If you don't do that, it's going to mess you up. Okay. All right. So is this balanced? No. I have 2 fluorines and 2 chlorines, so I would balance it by writing it that way. Okay, that would be a nonmetal replacing a nonmetal. All right. Okay, long video, sorry, but we're not even done yet because I didn't get to number 5 reaction type in the next video.